Welcome to the Alpha Training and Consulting's online training program. Today's discussion is entitled the Normality Plot MiniTab module. The purpose of this module is to teach the student how to use MiniTab to validate data set distributions, specifically the normal distribution, to define the various tests available for testing normality assumption, and to help the student understand if data is good enough to solve various process problems using the p-value and the fat pencil test. All right, let's get started. First of all, you have to understand what the normality plot is. The normality plot has this straight line right here, as you can see, and you put your data in the program, which I'll show you how to do, and it analyzes it and puts it on this straight line, or shows how it deviates from the straight line. If it's on a very straight line like this one is, for example, then it's considered to be normally distributed. It suggests that the data is normally distributed, which is what we want in most cases, because one of the most common assumptions in statistical analysis in Six Sigma projects anyway is normally distributed data. So it's a very important test to know how to do. Now this is what a negative distribution looks like. It's going on kind of straight, then it drops off the tail. And that suggests a negatively skewed distribution. And if it goes the other way, it kind of goes up on the top here, so it starts out straight and then goes up. That suggests a positively skewed distribution. And if it takes on kind of a, not real aggressive, but kind of an S shape, that suggests a rectangular distribution. Anyway, this is a very important module for applying what you learn about statistics into the real world. You can't just assume something is normally distributed. You must show that it's normally distributed. So let's get started, and I'm using MiniTab here. And to begin with, it's you just put in your title. So open up MiniTab and put in the title. So I'm going to do a little study on truck gas mileage. I collected some data from that so we could use it. And so enter the title, then you enter the data. There it is. I got 18.1 miles per gallon on that tank there, etc. 19.27. You can see all those different miles per gallon. The next step is you go to stat. So step number one is go to stat. And you may want to print this out as you do this for the first time, or have it on another screen so you can watch it and see what you're doing. The goal here is for you to learn how to use MiniTab. I'm not making you an expert at MiniTab. I'm getting you to the point where you can do your first project, okay? And if I can get you to that point, it's not hard to evolve and learn more and more. MiniTab's help menu is one of the better menus. So I'll most certainly get you started on this, but that's how you get going. You take across the tab up there called Stat, and you select that. That gives you this drop down, and you select Basic Statistics. By selecting, you just put your arrow there, it'll turn blue, and then you have to come over and go down. And if it takes students a while sometimes to get this down, because they'll go over here, they'll move too fast or whatever, and this will come back up. Anyway, you go over here to Basic Statistics, drag your mouse over, then go down to the normality test. And that's where we're going to check for normality, is with this test right here. So it's pretty simple. A little bit of practice and you'll get feeling comfortable with it. Then this will pop up, and at first you may not see anything in this column. If I have data down here in this spreadsheet type thing, they call them worksheets, worksheet, I may have this whole thing filled up with data, all the columns. Well, all those will show up with the titles of the columns right here. I only have one here today, so you only see one. If it's not showing up here, it's because you need to click on this box. So click in the variables box, and this will show up all of a sudden. Then you'll come over here, put your arrow there, double click on this, and it'll put the data right over here where you need it in this box. Once you get it in this box, this tells you this is the data set that you're analyzing, which of course I only have one. It's going to be truck gas mileage. And so there you go. Once you get to that, you just double click and it'll put the data right here where you need it. And now you're ready to go and analyze this thing. Then there's 3 different tests: Anderson-Darling, Ryan Joyner, and Kolmogorov, I guess. I'm not sure on that one. Now, different companies prefer different tests. So if you're a consultant and you're going to um, use one of these, you may want to talk to the person. If there is a person around there that's maybe a VP of quality, say, oh no, we always just use the Ryan Joyner test. And that's okay. You just do what they want you to do. To me, they all give similar results, but they do approach the problem differently. So that's all I'd recommend. You just let them know, do you have a preference on the normality test? A lot of times you go into organizations, they don't know which one, so I usually just pick the first one there, Anderson Darling. But I'm okay with any of them. They all give similar results. Then I'm going to select OK. Of course, I also put in the title. So, test for normality on truck gas mileage. And then I'm going to select OK. And then it will pop up with a graph here, and this is your normality plot. And this data, I know from experience, wow, this looks really quite great data. There's a little outlier here. I probably drove more in the city, or even more likely, probably that's when one of my teenage kids drove it. And the gas mileage kind of dropped off there. And then I have a couple here that are kind of out there a ways too. But this is all close to the straight line, so I have no problem using this data to do whatever analysis. The normality assumption is very valid here. And of course, if you're doing a Six Sigma project, you copy these graphs and put them in your PowerPoint. Now the p-value, this is interesting, but most people use a p-value of 5% or 0.05. If the p-value is over 0.05, it's considered to be acceptable in your normality for the 5% alpha risk type situation. So that's how that works. 40% is very high. So I wish all data was this great. As you'll see, it's just not the case. But the main thing when you look at data, you could have a statistician look at this and say, see these, how they kind of conglomerate and stack on top of each other? See those columns of numbers there? That suggests data stratification. So I have 3 stacked up, but if I had a more sensitive instrument, I may be able to, this one may actually be over here. But they stack up because your measurement system won't measure in those gaps. And so, but this isn't real bad. I'll show you some others where they're really stratified. But if you were real picky, you could say, it looks like there may be some stratification here. But all overall, this is very good data. Again, that's an outlier, that 18 point something there. But the rest of that looks real good. Am I going to change this data at all? No, not with a p-value of 40%. That's very good. All right. Now, also, just so you know, you can, in MiniTab, you can take your arrow and point it at this dot, and it will tell you what row that data comes from. So this one is from row 19. And so if I found that to be an outlier, I could go to row 19 and delete it by going, selecting that data point on row 19. And I'm going by memory here. But then you right click and you say delete cell, and it'll take that out for you. As you see, I did go through, it looks like, and maybe took some out here. I did. I took that outlier out, and it raised my p-value up to 53.9. Not that I need to do that. I'm just showing you how to do those types of things. If you get an outlier, you remove it, but you should record that you removed it. And if you're removing too many, something's wrong with the process, and you may want to go fix the process. Usually there's special causes, and it means you may need to go through the FMEA exercise, create the control plan, audit to the control plan, make sure everyone's doing the job the same so that you can create normal, predictable data. Okay, but there we have it, and let's go ahead and look next here. So notice I took out some replicated data points have been moved, so there's less stratification. That's where my p-value went up. Again, if I was to remove any, I would remove that 18 one there because that's a little bit out there. But everything else, I don't think we really need to touch this data up at all. It's a very good process. Okay, and remember, the help menu is always available. MiniTab has one of the greatest help menus of any program I use. In fact, if someone asks me a question on a statistic that I'm not sure about, I have plenty of textbooks, but I usually just go to MiniTab and go to the function I'm looking for, hit the help tab. It gives example problems and everything else. It's just really a great, great function, the help function. Now, what I'm doing here again is I'm teaching you the basics of MiniTab, how to do the basics so you can do your first project. From there, you can learn more about MiniTab with just the help menu. You could also go to a MiniTab class, and they do a great job as well. But the way I've learned over time, when I need help, I go here, I click help, I review it, I do maybe an example problem, and it's a great way to learn the material. It really is. Okay, so let's look at some examples. Here's a good example. Look how that is just great, great data. And I worked a project recently, and that was the actual data. That's just beautiful data. It's all on the line, no outliers. Your p-value's good. And so it's above 5%. Anything above 5 is good. And then I look to see how good it is. But this is beautiful data. Suggests it's very normally distributed. This is an example of very bad data. Okay, look at that. 2 straight lines and all these outliers. I don't know what went on there, but what could sometimes happens is they'll start it up. At startup, it doesn't work very well. And so all these points may be startups. If they are startups, when I hold my arrow there, it'll say, for example, row 18, row 19, row 20, row 21, row 22. In other words, they happen sequentially in time, one right after the other. And those, if you got rid of those and got rid of all of these, you may find out this one tilts over and is normally distributed. So you may be running different parts, and you have the machine set up differently, and you have some, when they start up, that gives you different values. And if you get rid of all the startups and just look at one part number, this may be normally distributed, and once you get rid of everything else, you may find this to be normally distributed. So usually if something is this bad, there's a reason for it. Of course, this one, if that's this is a straight line and you can't distinguish between them, then you have some major measurement resolution issues. What do I mean by measurement resolution? You measure it to the nearest inch, and you need to measure it to the nearest 10,000ths, okay? So when you measure it to the nearest inch, everything's the same value. And so that's the problem you see here. And of course, this p-value, when it says 0.005, something's greater than 0.05, it means that this is not normally distributed when it gives you that symbol. That's what I've learned. So very bad, out of control perhaps, or we just need to realize when they first start the machine up, it has problems. And that we're building, this data I got is from several different part numbers. 2 part numbers with startup issues. Get rid of the startup issues, get rid of the other part number. This could very well be normal. So anyway, it's very important to look at the data that way. And when you're doing this, I wouldn't just do a normality plot. I also do box plots and everything else, so I can see the data from a number of tools. I like to see things from multiple tools so I can feel comfortable that I have the full picture. All right, this suggests a positively skewed distribution. As you can see, the p-value is very terrible. And so this, again, I saw this on a project. You also have stratification issues. Looks how everything's stacked on top of each other. I mean, this one, look how you don't have any stacks, any clusters. They're just lined up. That means you have plenty of measurement resolution there. This one, they're stacked. So there's some resolution issues on this, among other things. Now, if you dug deeper, you may find that, again, I got data from 2 different part numbers. This part number and this part number. So there's many things you can investigate when things aren't normally distributed. Could I do anything with this data as is? No. This is pretty much garbage data. This is pretty much garbage data. When I go into a facility as a consultant and they're losing millions of dollars a month It's my job to figure out why. The first thing I do is I go get their data set and I see if I have good data or not. Usually what you'll find, you'll see some of these, some of these, some of these. And I can't do much with this, I can't do much with this. And when am I doing this? Usually when I'm on the airplane. They email me the data, I put it in MiniTab, I start looking to see what I have. And I separate the good from the bad. And this variable I'd say, hey, I hope this isn't your problem because you didn't collect good data. It's not predictable. And it's not measurable, so I can't do anything, I can't help you. The hope is they have good enough historical data that you can solve the problem with historical data. If they don't, you have to create data sets. And that's design of experiments, and it's going to cost the client a lot more money. If they have good data like this on all the important variables, I can solve the problem in most cases, oftentimes while you're on the plane. Okay, it's not, if you have the data, you can solve problems very quickly. The constraint on solving problems is data collection. That's why if you are in a position that you're responsible for getting good data, make sure you get good data. Make sure you get your processes in control so that when you have a problem, someone can come in and help you and solve the problem without creating new data. It costs money to create data. And anyway, it's very important. Here's another example. This is very good. The p-value is very good. It's above my 5% there, 0.05. There are some issues. Look at how they cluster together. That means your instrument resolution isn't probably where it should be. Maybe they're measuring with a caliper, and if they measured with a micrometer, you'd be able to measure in between these things better. Instead of having three clumped together, they'd be spread out more. But still, could I solve a problem with this? Yes. And that's how you should look at data. You can look at it as a statistician and say, the p-value, and I'm not saying that's bad, but at the end of the day, if you have a client that's losing millions of dollars worth of money a month off of a process problem, you need to say, okay, this isn't what I would like, but can I solve a problem with this? I've solved problems with some pretty shady data. And if you put on your stats hat, you'd say, no, you should not be doing that. Well, maybe I shouldn't, but I'm given no choice. These people are going to go bankrupt if I don't do something. So you look at the data from a slightly different perspective and say, you know, it's not great data, but I think I can solve a problem using it. And that's how I have to look at things. We don't live in a perfect world, trust me. Okay. Here's an example. I had this on when I was traveling on the airplane not too long ago, and very much that S-shaped, which suggests a rectangular distribution. Now sometimes things become rectangular because it's normally distributed, but they have a lot of, it's not a good process, and they've already inspected and they wipe out the tails of the distribution, and it'll show up looking something like this. So you want to ask them, now, does this data you gave me, does it come after inspection? If they say yes, you know why. Well, does that hurt me? Yes, it does, because I can't do much with this thing. This is very bad data. If you're using studies that assume a normal distribution, which a lot of them are. So here's some more. These are pretty typical that you'll see while you're flying on the airplane. Notice it's very normal, but look at the p-value. Isn't very good there on either one of them. And that's because of what? Stratification. Their measurement system isn't sensitive enough to pick up on the changes, and it clumps them together. Now, with that being said, do I think I could perhaps use this data, even though the p-value's low, to solve some problem that's may drive this customer into bankruptcy? Yes. I feel that I could on this stuff. I really do. It's not great, but I think it's good enough that I could solve it. So a lot of people would say, no, can't do this. And if you have that to do, you could say, okay, go use a micrometer instead of a caliper and gather the data again. Well, this data may have taken years to collect, and now they need to solve this problem overnight. I'm going to say, I think I can get this to work. If I have more time, I'll go have them use the micrometer instead of the caliper. It's all a matter of how much time you have. The goal, though, at the end of the day, why are we doing all this? to solve problems. And if you can use that to solve a problem, you should use it. Of course, here are some box plots and what have you. Just different ways to look at the data. And when you go into the normality plot, you can click some buttons so it creates all these graphs for you if you desire to have them. That just depends. If I'm in a big hurry and they have a lot of problems and a lot of data, I will probably not generate all these. I'll just look at these as a first sweep and try to decide where I'm at. Here's some other stuff I came across on the airport the other day. Look at the stratification problems here. That's terrible data. Okay, I may be able to do something with this. I cannot do anything with this. They're measuring and they don't have enough resolution at all. And so it created garbage data. Now, I'm not going to read through all these. I just put it on here for your reference. But you have the Anderson-Darling test, the Ryan-Joyner test, and the Kolmogorov test. And if you want to read about that, you most certainly can. However, I will say this. On all these tests, if the p-value of these tests is less than your chosen level, so if I choose 5%, 0.05, and it's below that level, you can reject your null hypothesis and conclude that the population is non-normal. So if it's below your p-value, that your critical p-value, then it's non-normal. If it's above it, you accept it as normal. And that's on all of these tests. This goes into a little greater detail. Again, I put that down there for your reference. I'm not going to read through all those. So you don't have to take off running on me. And I just wanted to remind you again, students struggle with this. If the p-value of these tests is less than your chosen level, which mine is usually 5%, that's pretty common, you can reject your null hypothesis and conclude the population is non-normal. And there I put it again. Why? Because I've taught this a lot. And students keep forgetting about that. So I hit it pretty hard. And there's the p-value. It's above my 5%. So this is great data. I'm actually surprised that it's not higher than that. So that's kind of curious to me. But it's a good example all the same. Now there's also a fat pencil test. And it's not quite as objective, but it's still what a lot of people do. And it's not bad. It's a very common test in Six Sigma. So what is it? An informal approximation of a normal test called the fat pencil test. Now that's pretty subjective. How fat are you going to make the pencil? And this is what it is. You just that's the fat pencil test. You put it over the data, and if it goes outside of it, you say, okay, it's not normal or it is normal. I look at both because, again, what am I trying to do? Ultimately, can I use this data in its imperfect form to solve a problem? If I can, good job, even if your p-value looks pretty bad. The goal is to, at the end of the day, is to solve a problem. Now, if you have a lot of time and you're setting up, maybe you're a manufacturing engineer, you may want to take the time to make sure you're measuring it right, and you should do that before you have a big problem. Because once you have a big problem, then you have to kind of use what's there. Before the problem, before the emergency, if you collect great data, it's going to pay off. Well, congratulations, you have almost completed this module. However, remember, you still need to complete the module exam as applicable. And I haven't decided, I may not even write an exam on this. This is more of an application module. But if you have any questions, please contact me and I'll get back with you as soon as possible. Thank you for joining me in this module. I hope you have learned something new that will enhance your career. Thank you, and goodbye.